The video for today's POTD, and I'll be doing yesterday's POTD because I missed it. So I'll be doing this one live. The previous one I already solved it. So yeah, this POTD I'll be doing it live. So where can I find it actually? Okay, so where is it? Yeah, already. Where can I see the problem? Oh yeah, there we go. Here. I think I missed this one. So let's just see what happens in this problem. I've already solved it, but I've solved it a while ago. I haven't solved a lot of problems in 2025, so I think it should be in 2024. So yeah, in a mystic dungeon, and magicians are standing in a line. Okay, each magician has an attribute that gives you energy. Some magicians can give you a negative energy, which means taking energy from you. You have been cursed in such a way that after absorbing the energy from the magician I, you will be instantly transported to magician I plus K. And this process will be repeated until you reach the magician I plus K, which does not exist. Okay, in other words, you will choose a starting point and then teleport with K jumps until you reach the end of the magicians, absorbing all the energy during the journey. So we are given an array and an integer K, and then we have to return the maximum possible energy that we can gain. Okay, so basically yeah. Okay, so basically we can start from any of the points, any of the i's, and then we have to jump K times, or basically we have to jump K positions x times, such that when we jump I plus x, I plus K, xth plus 1 time, we reach out of the array. That is what this problem says, and we can do this for every single index. So for example, in here they have used 2 plus 1 because that gives us 3. If we have used 5, then it would have been 5 plus minus 5, which will be a 0, and then if we have used minus 10, then it would be minus 10. So the maximum answer is 3. Okay, so this is basically like so we can reach a state. Okay. Yeah, sure. So what we can do here is basically okay. Okay. Yeah. So so we'll obviously be using all the energy that we have in one iteration. We have to add it to our current energy, right? So in here we can jump like that, and yeah. So okay, so we have two choices for a particular index, right? We can either start jumping from that index, or we can continue the jump from the previous iteration that we had, right? So this also screams TP. So yeah, basically what happens here is that basically we have two choices, right? So the first choice is we start a new jumping, I don't know, series or something from the current index. So that would mean that it would disregard all the choices that we had uh, that were related to jumping at the current index, right? Or the second choice that we have is we continue from previously I minus kth element. So yeah, I think this is pretty simple. Then it's just a normal DP. So what we can do here is basically we can have n as the energy of the size, and then obviously dp of 0 is equals to energy of 0. So yeah, we have that, and what we can do is we can start from I think 1, and yeah, we can actually do so basically 0 1 2 3 4 we can do 0 1 2 3, right? So we can just see that if I is greater than equals k, obviously, then well, concurrently the dp of I is equals to the energy of I, and then if that is true, then we can just do dp of I is equals to maximum of dp of I minus this is like that one thing that we have, the maximum sum. I forgot what it was called, the algorithm, but it's similar to this. We can also do it that way, but I believe that just using dp is more more intuitive in a way. So yeah, we can either do that, or we can just add it to our energy. add the previous dp of I minus k and the current energy, and then we can just return the maximum element inside our dp. So I think this is similar to that, you know, the subset sub array with maximum. It's something similar to that, maximum sub array, Caden's algorithm. So I think we can also optimize it with that, but this has an additional space complexity of O of n, I think. So yeah, okay, this is actually wrong. Let me check, why is it wrong? So we are doing when we are here we don't do it, when we are here we don't do it, when we are here, oh okay, oh okay. Well, it should be I minus k minus 1 0 1 2 2 2. Okay, no, I think that was fine. Okay, then we go here and we check, and then we go here, and how is it turning out to be? Let me just we can try to debug it. 2 10 0 minus 3. All right. Oh, okay. Well, oh, all right, I got it. If we start from somewhere, we obviously have to return the ending index, right? We can just return this. So yeah, that introduces, I think, some confusion in the problem. Yeah, cool. So what happened here was that I'm returning actually this energy of 0, which was 5, but what happens is that we have to continuously jump. So 5 will be jumping to -5, and then it will be a 0. So but my code is not accounting for that, so we only have to return the indexes that are at the end of the jumps, right? So yeah, so how can we check that? So we start, so basically yeah, so okay, so it's like this. Okay, let's just say we have 10 elements. Okay, and our k is let's just say it's I don't know, it's 3. Okay, so what are the positions that we can end in? So we can start from here, and then we can start from here, or basically we can jump here and then here, and then we can jump here, and then we can jump here, right? So we can end at this position, and then if we start from here we can jump here, and then we can jump here and end up in this position, and then if we start from here then we can jump, this is the same as oh yeah, this is different. So basically we can end up in all the positions that are basically we start from here and then coming here and then coming here. Yeah, okay, so we can basically end up at the positions that are yeah, so we can do one thing. We can just check like basically so 0 1 2 3 4, so 5 minus 3 0 1 2, so it starts with 2. Okay, 5 minus 3 is actually 2, I think so. So basically it should be if n minus I is less than or equal to k, then we can just do answer equals maximum of answer comma dp of I, and then we can just return the answer. Is this fine? I think this is fine. And then answer, we can just have a very negative value. I think this should work, I think, because we are considering now the only elements that are ending. This might also fail because then we have to debug it. Okay, it worked. Yeah, I used this to get, I don't really care. Okay, so it worked, but I think this has better solutions in a way, and we can actually read them. What were their hints? Yeah, okay. Yeah, so it's similar to what I have done. It's just the ending states are these, because why the ending states are these. Okay, yeah, I didn't justify why I did this. So basically, you can see here the example that I took. Oh, I deleted it. Should be here somewhere. Where's the example? Yeah, there it is. So basically what happens is that we are only going to end up in all of these states. Why that happens? Because that is actually a good proof that we can do. So basically why does that happen? We'll always end up in these states because let's just say that we are jumping k times, right? So every index will have certain mod. So let's just say that this current if we try to jump here, then we'll jump here next, and then we'll jump here next, and then we'll jump here next. So why did that happen? Because we're jumping k times from the first index, so that would actually end up at the last index. And if we try to jump from here, then we'll end up here, and then we'll jump here, then we'll end up here, and in certain way we'll always end up at the last positions that are modulo k. So for example, we are starting at the second position and we are ending here, right? So this position is actually 2, and 3 modulo 2 is yeah. So 3 modulo 2 is basically 1, and then we end up at positions k minus k modulo I in a way, such that I is less than k. This would only work in that way, but we don't really need to check for all the positions that have the mod of I k base. Oh, my bad. We don't really need to check for all the positions that are I and greater than k, because they'll actually be a part of the previous iterations. So we just need to check the ones that are less than k, and these are the ones. I don't know how to explain it. I mean, you can just draw cases and probably just see how it is working, but I believe that this is how you can do it. And last year I was doing it, so I had a lot of TLEs, so I've obviously improved. I don't know what I wrote here. Oh, I tried to do greedy and then just fucking failed, I think. Yeah, this is same, but now I'm just doing it in one iteration, so I think this code is pretty good. Yeah, I'll just paste it here if you want to see it. Yeah, I think I've improved it. I have really improved. I was using I was actually using DP, then I just gave up and just try to use. Yeah, okay, I was writing code. Yeah. Well, this is what we can do actually. So that's it. I think that's it about the problem. Goodbye.